Hello and welcome to my talk about eBPF, Innovations in Cloud Native. What is actually Cloud Native? There is in fact a definition from the CNCF, which says that Cloud Native computing is an approach in software development that utilizes cloud computing to build and run scalable applications in modern dynamic environments, such as public, private, and hybrid clouds. The techniques for that are loosely coupled so that you have resilient systems that are more manageable and observable. And the whole goal is to make high impact changes frequently and without disruption. I usually don't look at analyst reports, but it was interesting to see that by 2025, Gartner estimates that over 95% of new workloads, they're in a cloud native environment. And Kubernetes is in fact the pillar of cloud architectures and also used for cross-cloud orchestration. The cloud native embraces the container model. The container model is, essentially the single kernel becomes the common denominator. It has to manage a lot of networking objects like network namespaces, devices, sockets, as opposed to having full-blown VMs as in the past, right? The scale and scope is also changing. So while in the past there were a few VMs, now there are many containers. The container density on a node is high to maximize the resource usage of a machine. The lifetime of a container becomes shorter. With that, also higher IP churn. In general, the trend is to move to generic worker nodes with co-located specialized functions, like your whole cluster becomes a load balancer as well. The challenges don't just stop there. So once you have your initial cluster up in Bootstrap, there are day 2 challenges that we call. It's mainly around integration with external workloads. For example, when you don't just move to a cloud native environment with a flick of a switch, but it's a successive step, and that also requires to interconnect with other existing workloads through more predictable IP addresses. Successive migration to IPv6 only clusters is a topic because Kubernetes supports it and it allows for more IPAM flexibility. With that comes also the need for NAT4664 to interact with IPv4 based workloads. And once you have multiple clusters, now the question is how to connect them together in a scalable way. Topology-aware routing is a big issue around that, also traffic encryption between those clusters. And observability, especially scalable observability, in order to detect or troubleshoot issues in the cloud environment. Scalable network and runtime security enforcement is important, and of course, an improved networking throughput and latency. What about the building blocks? Well, the kernel, as usual, is the foundation. Given the applications, they use sockets as data source and sinks, and the kernel becomes the common denominator. The networking is the communication bus around that, and typically the Linux kernel and Kubernetes together is seen as the Cloud OS. There are many building blocks. A lot of them have been designed more than 10 years ago, and they're often loosely coupled, which means those individual subsystems, they don't talk with each other. They're like some of them are inflexible, which only allow for global node policies, but not per container policies. Or some of them are inefficient simply because they have been designed back then, and back then it was good enough. But the typical example here is the list style processing that we see with IP tables. On the right side here, I posted an IP tables dump from kubeproxy when there are many services connected in the cluster. And also there's no pod awareness. So really, if developers want to provide tools for cloud native environment, they're stuck in this box, and a lot of those things, they cannot be expressed efficiently for modern environments. So how does eBPF come into play as a cloud native tool, and what innovations does it bring along with that? First of all, eBPF is a framework to extend US kernel. It's a general purpose engine with a minimal instruction set, and it allows for running programs in the kernel to customize its behavior without changing the source code. Those programs, they can be updated on the fly without node reboot, for example, or even workload disruption. They're verified for safety, so they don't crash the kernel or make it unstable. And those programs can also be made portable between different kernel versions. And what you can see then is you can shift context from user space, from Kubernetes into the kernel thanks to BPF. And I now want to talk about 10 innovations that I think that eBPF brought to the table, along with its framework So number one, BPF allows to significantly speed up the development. I think that's really important because if you think of a typical patch life cycle, you need to develop the patch, get it merged upstream, then you need to wait until major distributions get released with it, but it doesn't just stop there because also users, they have to adopt it. And typically what we see is users, they like to stick to LTS kernels, understandably, and they have like a 2-year release cadence, which is really long. So if there is if in the old model innovation should happen and it's needed in the kernel, then that usually required to change the kernel itself or to build kernel modules, and that leaves most of the community out. And with this long release cadence, there's minimal or no feedback loop from developers to users. And BPF really helped to break this long cycle here because it managed to decouple from kernel releases. Just think about, for example, Cilium, when it installs its networking programs, we don't necessarily care too much around the kernel versions. What runs on older kernels can also run on newer ones, and it can bring this change instantly just by upgrading Cilium itself, but not the kernel. Number two, BPF allows to shift data processing closer to the source, freeing up resources. If you think about traditional networking functions like load balancer, firewalls, etc., they are on a per packet basis. This comes more like traditionally from the hardware style processing that has been moved then into software. But it can be expensive, as in particular on generic layers of the kernel where every packet needs to be inspected and modified. But if we reframe the original problem by moving further up or down the stack, essentially as close to the source as possible, we also get more OS context around that. And BPF allows really to shift the networking processing into the socket layer, or into C group layer, or really down into the driver, into the express data path layer. And that really helps to significantly save costs because of that. Number three, BPF allows for shorter production feedback loops and location-aware processing as well. If you think back, like if you run your own kernel in your fleet, if you have that luxury, and if you let's say, for example, want to experiment with congestion controls in order to optimize this for your data center, it's a long feedback loop because you need to patch that kernel, you need to gradually roll it out to deploy the change, and only then you can start experimenting, collecting data, and then you need to start over. It's like an iterative process. It's long, fragile, because traffic needs to be drained from nodes. Nodes need to be restarted. You're unable to move fast. And the same principle of the decoupling from the kernel version, it allows for much faster updates of the program, and this shortens the feedback loop. Number four, BPF enables to move traffic with significantly lower latency. So that allows essentially to implement node local forwarding infrastructure for data center workloads with the TC BPF layer in particular. The usual traditional way is to move, like when packets to and from the pods into host namespace, is usually going through upper layers of the stack. And because of that, some of the information on the packet is lost. If we can retain all of this in the TC BPF layer, we can do all the forwarding in a low layer, and with that, information can be retained from the packet, such as the packet socket association or egress timestamps. And the whole theme around this is to get host native performance for pods, for network namespaces, essentially. And this really helps around the feedback for TCP. It helps TCP pacing, BBR, which is based on top of that, and various other things. And this all ties into reducing buffer bloat, not only for the host, but for pods in particular. Number five, BPF provides building blocks from the kernel instead of just reinventing the wheel. And that really, the perfect example around this is the FIP lookup helper, because it allows to reuse kernel routing and neighbor tables. All of the user space BGP stacks, they can transparently be reused because the routes can be installed through netlink into the kernel, and BPF from a fast path, for example, out of the XDP layer, has the ability to just look up the existing kernel routing tables, and you can build high performance routers with that. Also in going into number 5, it provides building blocks which are otherwise too complex for other kernel subsystems. For example, NetFilter never had a NAT4.6 and 6.4 translation possibility. Typically, the IPv4 and IPv6 code base is very complex, and a lot of the packet representation, from the SKB in the kernel, it contains address family specific data, and it's hard to change, hard to manage. There are some existing out of kernel tree modules around NAT4.6, 6.4, but they never made it upstream. They all had their limitations. We implemented this with BPF, and it's, I would say, reasonably straightforward. Around XTP, because there's no context, it's in the earliest possible layer. It can just be done through rewriting the packet and push it back out, for example, for gateways. Around the TCBPF layer, there's a small helper which changes the metadata around the socket buffer, and the rest of the rewrites they're done in the BPF program, but it's definitely possible and easier to do than in other subsystems. Good example around this is also Android. So they use this today on your phone to connect to IPv6 only cell networks. Number 6, BPF to some degree at least allows to fix or mitigate kernel bugs on the fly. So there was a good example earlier in this year around that where we fixed the kernel bug inside the Weave driver, and that actually affected on AWS the physical devices transmit queue selection. There's a good talk around this tomorrow from Laurent. All your queues belong to us. I recommend you dial into that as well. And that helped to avoid complex rollout of new kernels. And this time it was out of the user's hand. So even if the infrastructure team don't build their own kernel, then you need to wait for the cloud provider to actually pull in the stable fix and to update it. And like this, you can just do a change in BPF and restart the application, and that's it, right? Then the bug is fixed, and you can plan a proper upgrade later on. The other thing that is less talked about is resilient receive processing to actually reduce the attack surface of the stack from bad actors. Good example here is flow dissector, which can be implemented or partially implemented in BPF and XTP to help to drop packets early that would otherwise cause a packet of death type scenario in the upper stack when it does complex packet parsing. Number 7, BPF allows for low overhead deep visibility and enforcement into the system. So I could probably do like a whole hour talk about this topic, but essentially the gist is that for your cloud native environment, you can run the BPF collectors on every node, they gather interesting data, and then they can be pushed into a store and then visualized through nice dashboards. So I think that's super interesting. There are many projects around that, in fact, already. The other thing is troubleshooting production issues on the fly, especially in a safe way with BPF. There are a good number of BPF trace examples around this, and it provides richer visibility than the old style perf. Another example in tracing and security enforcement that we can do, I posted here like a configuration around Tetragon where it can kill processes that would create unprivileged user namespaces. So that's a possibility. The other one is, the data export and into GUI dashboards where you get the visibility in a nice way and can inspect your cluster in a deeper level. Number 8, BPF decouples from legacy UAPI and allows for efficient data processing. So traditionally in the kernel, things had to be extended and oftentimes touching the fast path, where the feature itself may only have been applicable to a small subset of users, but BPF allows to keep the fast path to minimum and actually fast, because it decouples if users have to solve a complex problem, it can just be done in BPF without actually affecting the kernel's UAPI that it exports, right? And there are building blocks like helpers maps to and they even decoupled the entry point into BPF. So the entry point to keep that efficient is the most crucial one, and everything else is then up to the user to implement. In the case of, just to provide an example here, the whole queue proxy replacement we built around BPF, so it's possible to build a fully conformant, even more efficient and customizable thing with just the eBPF compared to NetFilter. Number 9, BPF is an enabler to build policy enforcement features around stronger notion of identity. So that's the whole core around abstracting away from this high IP churn in crucial Kubernetes environments. So IPs, they become meaningless because most of the pod configurations in Kubernetes, they are centered anyway around pod labels. And the other thing is, the general pod lifetime is becoming shorter, so there are ephemeral workloads. BPF helps you to build policy around labels in an efficient way, and also to build things like egress gateways where you move away, where you can build like more stable IPs, which can then connect to the outside world, or like to the rest of the environment, where, for example, ACLs are hard to update or to keep up with this churn. Number 10, BPF allows developers to extend the kernel, but with a safety belt on. I think that's probably the most important feature where the BPF brings to the table. If you think about developing kernel code and developing the same code actually in BPF to say the same functionality, the cost around the BPF is much lower, simply because of the built-in safety from the verifier. It helps to troubleshoot production environments, which can be stressful, but with the safety belt on, it's easier, and it's easier to debug things. Portability can be achieved for BPF modules across kernel versions. There are built-in features into BPF such as Cori, BTF, and so on. So BPF really becomes a flavor of the C language that is a better and safer choice for programmers. There's a good example that has been shown at LPC, where like a code snippet that is okay in C but not okay in BPF C, because the verifier also takes type information into account, and if there's no safe access that is determined, then the program is simply rejected. So what comes next? Around the BPF core, that we will see more building blocks and lower entry barrier for developers. We're already on our way to support 100% of C in a safe way. Use cases are typically production need driven. So whenever something comes up that needs to be solved, typically also pushes the boundaries of the BPF core. So we extend the infrastructure around that. For example, that what will be possible soon is to implement data structures natively with BPF, or to have programs at early boot time, just to provide 2 examples. The other thing is cross-platform support and standardization. So eBPF Foundation is working around providing a BPF specification. Number 2, signing is a big topic in BPF. So the main goal is to attest the origin and to verify if the source is actually authorized to run BPF programs. Whole goal is to keep bad actors out, while also clearly identifying the actors that are using BPF, the good actors. The challenge here is to that the vast majority of programs in the ecosystem are actually of dynamic nature. For example, just think of BPF trace, and signing only static programs would lock out the vast majority of those users and would break those. So that's definitely a no-go. And there are various approaches in the discussion. There's no good one-size-fits-all type solution for covering all of them. Right now, what we are approaching towards is a gatekeeper BPF program that can be hooked into the verifier at various points to do the signature verification, and then use reuse the in-kernel key management facilities for that as well. And the other one is the signatory service for the BPF ecosystem in order to solve this dynamic nature of the programs. There's definitely also high interest from not only Linux, but also the Windows community. Next topic is the increased focus on profiling BPF with BPF. So the more components in your cloud native environment are run with BPF doesn't automatically mean it gets faster. For example, badly written programs, they of course can cause performance regressions, cache misses, and so on. So more visibility and profiling eBPF becomes increasingly important. There are already some work around this. some initial tools around that topic, but we'll definitely see more, for example, code coverage for BPF programs. Cloud native environments, they see even bigger adoption. So I think similar as Kubernetes fans out into edge environments, so does also BPF. BPF also already gets implemented for 5G data planes. We see it in IoT security enforcement environments, but there's more coming around APMs, security monitoring platforms, not only load balancers, but also gateways into the cloud. There's a lot of potential around memcaches and accelerators. There have been some work in academia around that, but not yet some public or at least OSS projects. What is also really funny at the LPC conference recently, I overheard that XDP and BPF is actually already running in wind turbines. We'll definitely see adoption growing in more conservative environments, such as ISPs and telco environments, simply because XDP and AFXDP, together with BPF, they blend in more naturally with Kubernetes as opposed to, for example, frameworks like DBDK, simply because it's easier to configure, to use, and the context is already in the kernel. So when something has to be pushed into a pod, it's already in kernel space and doesn't have to be pushed from user space back into the kernel just to reach sockets. There's also a lot of interest around BPF and SRv6 for traffic engineering. And if you think about the initial Gartner statement with regards to Kubernetes mainstream adoption, the more users are migrating towards Kubernetes, also BPF solutions piggyback on that because they are already the preferred choice or default today. And there's a strong and continuous growth of existing, but also new areas. So there are new use cases on the horizon, such as the process scheduler, where 3 companies are actually working on that. BPF for file integrity monitoring and system to monitor system software and applications as well is interesting. A lot of the potential BPF also has around storage. There are some early discussions around that in work, but I expect more to come in this area too. More longer term directions, so BPF usage as safe and portable kernel modules. There are some users already that set precedents here. For example, the human interface devices that are being merged right now as we speak. But once that happens, I definitely expect other areas as well to where this grows. Live patching could be an opportunity that's a bit further out in the future, I think. But what I also think from project side that is really interesting is projects like Kepler that already use BPF to export power consumption data for Kubernetes clusters. I think that also is really interesting to later on tie this into other layers as well, such as BPF process schedulers. So I think there's a lot of new things and exciting things to come in the future. And with that, I would like to thank you and open up for questions. Thanks.